Hey YouTube, what's up? Well, I'm currently working on a standard in artificial intelligence, namely Grid World, which enables one to learn what reinforcement learning and coding therein is all about. This is just a necessary step to graduate from coding via Q-learning and its table lookup environment to deep Q networks introduced by DeepMind in their 2015 seminal paper in Nature. So let's take a look at DeepMind's website that introduces this. Human level control through deep reinforcement learning. This paper, published in Nature on the 26th of February 2015, describes a deep RL system which combines deep neural networks and reinforcement learning at scale for the first time, and is able to master a diverse range of Atari 2600 games to superhuman level with only the raw pixels and score as inputs. For artificial agents to be considered truly intelligent, they should excel in a wide variety of tasks that are considering challenging for humans. For artificial agents to be considered truly intelligent, they should excel at a wide variety of tasks that are considered challenging for humans. Up till this point, it had only been possible to create individual algorithms capable of mastering a single specific domain. With our algorithm, we leveraged recent breakthroughs in training deep neural networks to show that a novel end-to-end reinforcement learning agent, termed a deep Q network, DQN, was able to surpass the overall performance of a professional human reference player and all previous agents across a diverse range of 49 game scenarios. DeepQN is a specialized subfield of deep reinforcement learning, an area of AI that is gathering much interest and enthusiasm today. While Q-learning is not very difficult to master, DQN requires the capability of being able to code at least an artificial neural network, ANN. Something I found extremely difficult to divine until I came across the YouTube lecture series published by Welch Labs in 2014. So if I can learn to code an ANN, you too will be able to after going through the 4-part series I'm about to bring to you.
Y given some input value x. For example, predict some output value y given some input value x. Let's say you want to predict some output value y given some input value x. For example, maybe you want to predict your score on a test based on how many hours you sleep and how many hours you study the night before. To use a machine learning approach, we first need some data. Let's say for the last 3 tests, you recorded your number of hours studying, your number of hours sleeping, and your score on the test. We'll use the programming language Python to store our data in 2-dimensional NumPy arrays. Now that we have some data, we're going to use it to train a model to predict how well you'll do on your next test based on how many hours you sleep and how many hours you study. This is called a supervised regression problem. It's supervised because our examples have inputs and outputs. It's a regression problem because we're predicting your test score, which is the continuous output. If we were predicting your letter grade, this would be called a classification problem and not a regression problem. There are an overwhelming number of models within machine learning. Here, we're going to use a particularly interesting one called an artificial neural network. These guys are loosely based on how the neurons in your brain work and have been particularly successful recently at solving really big, really hard problems. Before we throw our data into the model, we need to account for the differences in the units of our data. Both of our inputs are in hours, but our output is a test score scaled between 0 and 100. Neural networks are smart, but not smart enough to guess the units of our data. It's kind of like asking our model to compare apples to oranges, or most learning models really only want to compare apples to apples. The solution is to scale our data. This way our model only sees standardized units. Here, we're going to take advantage of the fact that all our data is positive and simply divide by the maximum value for each variable, effectively scaling our result between 0 and 1. Now we can build our neural net. We know our network must have 2 inputs and 1 output because these are the dimensions of our data. We'll call our output layer y hat because it's an estimate of y, but not the same as y. Any layer between our input and output layer is called a hidden layer. Recently, researchers have built networks with many hidden layers. These are known as deep belief networks, giving rise to the term deep learning. Here we're going to use 1 hidden layer with 3 hidden units. But if we wanted to build a deep neural network, we would just stack a bunch of these layers together. In neural net visuals, circles represent neurons and lines represent synapses. Synapses have a really simple job. They take a value from their input, multiply it by a specific weight, and output the result. Neurons are a little more complicated. Their job is to add together the outputs from all their synapses and apply an activation function. Certain activation functions allow neural nets to model complex, nonlinear patterns that simpler models may miss. For our neural net, we'll use sigmoid activation functions. Next, we'll build out our neural net in Python. Last time, we set up our neural network on paper. This time, we'll implement it in the programming language Python. We'll build our network as a Python class, and our init method will take care of instantiating important constants and variables. We'll make these values accessible to the whole class by placing a self dot in front of each variable name. Our network has 2 inputs, 3 hidden units, and 1 output. These are examples of hyperparameters. Hyperparameters are constants that establish the structure and behavior of our network, but are not updated as we train the network. Our learning algorithm is not capable of, for example, deciding that it needs another hidden unit. This is something that we must decide on before training. What neural networks do learn are the parameters, specifically the weights on the synapses. We'll take care of moving our data through our network in a method called forward. Rather than pass inputs through the network one at a time, we're going to use matrices to pass through multiple inputs at once. Doing this allows for big computational speedups, especially when using tools like MATLAB or NumPy. Our input data matrix X is of dimension 3 by 2 because we have 3 two-dimensional examples. Our corresponding output data, Y, is of dimension 3 by 1. Each input value, or element in matrix X, needs to be multiplied by a corresponding weight and then added together with all the other results for each neuron. This is a complicated operation, but if we take the 3 outputs we're looking for as a single row of a matrix, and place all our individual weights into a matrix of weights, we can create the exact behavior we need by multiplying our input data matrix by our weight matrix. Using matrix multiplication allows us to pass multiple inputs through at once by simply adding rows to the matrix X. From here on out, we'll refer to these matrices as X, W1, and Z2, where Z2 is the activity of our second layer. Notice that each entry in Z is a sum of weighted inputs to each neuron. Z is of size 3 by 3, 1 row for each example, and 1 column for each hidden unit. We now have our first official formula. Z2 is equal to X times W1. Matrix notation is really nice here because it allows us to express the complex underlying process in a single line. Now that we have the activities of our second layer, Z2, we need to apply the activation function. We'll independently apply the function to each entry in matrix Z using a Python method for this called sigmoid, because we're using a sigmoid as our activation function. Using NumPy is really nice here because we can pass in a scalar, vector, or matrix. NumPy will apply the activation function element-wise and return a result of the same dimension as it was given. We now have our second formula for forward propagation. Using f to denote our activation function, we can write that A2, our second layer activity, is equal to f of Z2. A2 will be a matrix the same size as Z2, in this case 3 by 3. To finish forward propagation, we need to propagate A2 all the way to our output y hat. We've already done the heavy lifting in our previous layer, so all we have to do now is multiply A2 by our second layer weights W2 and apply one more activation function. W2 is of size 3 by 1, one weight for each synapse. Multiplying A2, a 3 by 3, by W2, a 3 by 1, results in a 3 by 1 matrix Z3, the activity of our third layer. Z3 has 3 activity values, one for each example. Last but not least, we'll apply our activation function to Z3, yielding our official estimate of your test score, y hat. We need to implement our forward propagation formulas in Python. First, we'll initialize our weight matrices within our init method. For starting values, we'll use random numbers. We'll implement forward propagation in our forward method, using NumPy's built-in dot method for matrix multiplication and our own sigmoid method. And there you have it, a Python class capable of estimating your test score given how many hours you sleep and how many hours you study. We can pass in our own input data and get real outputs. Now, you may be noticing that our estimates are quite terrible. That's because we have not yet trained our network, and that's what we're going to work on next time. Last time, we built a neural network in Python that made really bad predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. This time, we'll focus on the theory of making those predictions better. We can initialize the network we built last time and pass in our normalized data x using our forward method, and have a look at our estimate of y hat. Right now, our predictions are pretty inaccurate. To improve our model, we first need to quantify exactly how wrong our predictions are. We'll do this with a cost function. A cost function allows us to express exactly how wrong or costly our model is, given our examples. One way to compute an overall cost is to take each error value, square it, and add these values together. Multiplying by 1/2 will make things simpler down the road. Now that we have a cost, our job is to minimize it. When someone says they're training a network, what they really mean is that they're minimizing a cost function. Our cost is a function of two things: our examples and the weights on our synapses. We don't have much control over our data, so we'll minimize our cost by changing the weights. Conceptually, this is a pretty simple concept. We have a collection of 9 individual weights, and we're saying that there is some combination of w's that will make our cost, j, as small as possible. When I first saw this problem in machine learning, I thought, I'll just try all the weights until I find the best one. After all, I have a computer. Enter the curse of dimensionality. Here's the problem. Let's pretend for a second that we only have one weight instead of 9. To find the ideal value for our weight that will minimize our cost, we need to try a bunch of values for w. Let's say we test 1,000 values. That doesn't seem so bad. After all, my computer is pretty fast. It takes about 0.04 seconds to check 1,000 different weight values for our neural network. Since we've computed the cost for a wide range of values of w, we can just pick the one with the smallest cost, let that be our weight, and now we've trained our network. So you may be thinking that 0.04 seconds to train a network is not so bad, and we haven't even optimized anything yet. Plus, there are other way faster languages than Python out there. Before we optimize, though, let's consider the full complexity of the problem. Remember, the 0.04 seconds required is only for one weight, and we have 9 total. Let's next consider 2 weights for a moment. To maintain the same precision, we now need to check 1,000 times 1,000 or 1,000,000 values. This is a lot of work even for a fast computer. After our 1,000,000 evaluations, we found our solution, but it took an agonizing 40 seconds. The real curse of dimensionality kicks in as we continue to add dimensions. Searching through 3 weights would take 1,000,000,000 evaluations, or 11 hours. Searching through all 9 weights we need for our simple neural network would take 1,268,399,679,350,583.5 years. For that reason, the just try everything or brute force optimization method is clearly not going to work. Let's return to the one-dimensional case and see if we can be more clever. Let's evaluate our cost function for a specific value of w. If w is 1.1, for example, we can run our cost function and see that j is 2.8. We haven't learned much yet, but let's try to add a little more information to what we already know. What if we could figure out which way was downhill? If we could, we would know whether to make w smaller or larger to decrease the cost. We could test the cost function immediately to the left and to the right of our test point and see which is smaller. This is called numerical estimation and is sometimes a good approach, but for us there's a better way. Let's look at our equations so far. We have 5 equations, but we can really think of them as one big equation. And since we have one big equation that uniquely determines our cost j from x, y, w1, and w2, we can use our good friend calculus to find exactly what we're looking for. We want to know which way is downhill. That is, what is the rate of change of j with respect to w, also known as the derivative. And in this case, since we're just considering one weight at a time, this is a partial derivative. We can derive an expression for dj/dw that will give us the rate of change of j with respect to w for any value of w. If dj/dw is positive, then the cost function is going uphill. If dj/dw is negative, then the cost function is going downhill. Now we can really speed things up. Since we know in which direction the cost decreases, we can save all the time that we would have spent searching in the wrong direction. We can save even more computational time by iteratively taking steps downhill and stopping when the costs stop getting smaller. This method is known as gradient descent, and although it may not seem so impressive in one dimension, it is capable of incredible speedups in higher dimensions. In fact, in our final video, we'll show that what would have taken 10 to the 27th function evaluations with our brute force method will take less than 100 evaluations with gradient descent. Gradient descent allows us to find needles in very, very, very large haystacks. Now, before we celebrate too much here, there is a restriction. What if our cost function doesn't always go in the same direction? What if it goes up and then back down? The mathematical name for this is non-convex, and it could really throw off our gradient descent algorithm by getting it stuck in a local minimum instead of our ideal global minimum. One of the reasons we chose our cost function to be the sum of squared errors was to exploit the convex nature of quadratic equations. We know that the graph of y equals x squared is a nice convex parabola, and it turns out that higher dimensional versions are too. Another piece of the puzzle here is that depending on how we use our data, it might not matter if our function is convex or not. If we use our examples one at a time instead of all at once, sometimes it won't matter if our function is convex. We will still find a good solution. This is called stochastic gradient descent. So maybe we shouldn't be afraid of non-convex loss functions, as neural network wizard Yann LeCun says in his excellent talk, Who is Afraid of Non-Convex Loss Functions? The details of gradient descent are a deep topic for another day. For now, we're going to do our gradient descent batch style, where we use all our examples at once, and the way we've set up our cost function will keep things nice and convex. Next time, we'll compute and code up our gradients. Last time, we decided to use gradient descent to train our neural network so it could make better predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. To perform gradient descent, we need an equation and some code for our gradient dj/dw. Our weights w are spread across 2 matrices, w1 and w2. We'll separate our dj/dw computation in the same way. by computing dJDW1 and dJDW2 independently. We should have just as many gradient values as weight values, so when we're done, our matrices, dJDW1 and dJDW2, will be the same size as W1 and W2. Let's work on dJDW2 first. The sum in our cost function adds the error from each example to create an overall cost. We'll take advantage of the sum rule in differentiation, which says that the derivative of the sums equals the sum of the derivatives. We can move our sigma outside and just worry about the derivative of the inside expression first. To keep things simple, we'll temporarily forget about our summation. Once we've computed dJDW for a single example, we'll go back and add all our individual derivative terms together. We can now evaluate our first derivative. The power rule tells us to bring down our exponent 2 and multiply. To finish our derivative, we need to apply the chain rule. The chain rule tells us how to take the derivative of a function inside of a function, and generally says that we take the derivative of the outside function and multiply it by the derivative of the inside function. One way to express the chain rule is as the product of derivatives. This will come in very handy as we progress through backpropagation. In fact, a better name for backpropagation might be, don't stop doing the chain rule ever. We've taken the derivative of the outside of our cost function. Now we need to multiply it by the derivative of the inside. Y is just our test scores, which won't change, so the derivative of y, a constant, with respect to w is 0. Y hat, on the other hand, does change with respect to w2, so we'll apply the chain rule and multiply our results by minus dy hat dw2. We now need to think about the derivative of y hat with respect to w2. Equation 4 tells us that y hat is our activation function of z3, so it will be helpful to apply the chain rule again to break dy hat dw2 into dy hat dz3 times dz3 dw2. To find the rate of change of y hat with respect to z3, we need to differentiate our sigmoid activation function with respect to z. Now is a good time to add a new Python method for our derivative of our sigmoid function, sigmoid prime. Our derivative should be largest where our sigmoid function is the steepest, at the value z equals 0. We can now replace dy hat dz3 with f prime of z3. Our final piece of the puzzle is dz3 dw2. This term represents the change of z, our third layer activity, with respect to the weights in the second layer. z3 is the matrix product of our activities, a2, and our weights, w2. The activities from layer 2 are multiplied by their corresponding weights and added together to yield z3. If we focus on a single synapse for a moment, we see a simple linear relationship between w and z, where a is the slope. So for each synapse, dz dw2 is just the activation a on that synapse. Another way to think about what the calculus is doing here is that it is backpropagating the error to each weight. By multiplying by the activity on each synapse, the weights that contribute more to the overall error will have larger activations, yield larger dJDW2 values, and will be changed more when we perform gradient descent. We need to be careful with our dimensionality here, and if we're clever, we can take care of that summation we got rid of earlier. The first part of our equation, y minus y hat, is of the same dimension as our output data, 3 by 1. F prime of z3 is of the same size, and our first operation is a scalar multiplication. Our resulting 3 by 1 matrix is referred to as the backpropagating error delta 3. We determined that dz3 dw2 is equal to the activity of each synapse. Each value in delta 3 needs to be multiplied by each activity. We can achieve this by transposing A2 and matrix multiplying by delta 3. What's cool here is that the matrix multiplication also takes care of our earlier omission. It adds up the dJDW terms across all our examples. Another way to think about what's happening here is that each example our algorithm sees has a certain cost and a certain gradient. The gradient with respect to each example pulls our gradient descent algorithm in a certain direction. It's like every example gets a vote on which way is downhill, and when we perform batch gradient descent, we just add together everyone's vote, call it downhill, and move in that direction. We'll code up our gradients in Python in a new method, cost function prime. NumPy's multiply method performs element-wise multiplication, and the dot method performs matrix multiplication. We now have one final term to compute, djdw1. The derivation begins the same way as before, by computing the derivative through our final layer. First dj dy hat, then dy hat dz3. We now take the derivative across our synapses, which is a little different from our job last time, which was computing the derivative with respect to the weights on our synapses. There's still a nice linear relationship along each synapse, but now we're interested in the rate of change of z3 with respect to a2. Now the slope is just equal to the weight value for that synapse. We can achieve this mathematically by multiplying by W2 transpose. Our next term to work on is dA2 dz2. This step is just like the derivative across our layer 3 neurons, so we can just multiply by f prime of z2. Our final computation here is dz2 dw1. This is very similar to our dz3 dw2 computation. There is a simple linear relationship on the synapses between z and w1. In this case, though, the slope is the input value x. We can use the same technique as last time and multiply by x transpose, effectively applying the derivative and adding our djdw1s together across all our examples. All that's left is to code this equation in Python. What's cool here is that if we want to make a deeper neural network, we could just stack a bunch of these operations together. So how should we change our w's to decrease our cost? We can now compute djdw, which tells us which way is uphill in our 9-dimensional optimization space. If we move this way by adding a scalar times our derivative to all of our weights, our cost will increase. And if we do the opposite, subtract our gradient from our weights, we will move downhill and reduce our cost. This simple step downhill is the core of gradient descent, and a key part of how even very sophisticated learning algorithms are trained. Next time, we'll perform numerical gradient checking to make sure our math is correct. Last time, we did a bunch of calculus to find the rate of change of our cost, j, with respect to our parameters, w. Although each calculus step was pretty straightforward, it's still relatively easy to make mistakes. What's worse is that our network doesn't have a good way to tell us that it's broken. Code with incorrectly implemented gradients may appear to be functioning just fine. This is the most nefarious kind of error when building complex systems. Big, in-your-face errors suck initially, but it's clear that you must fix this error for your work to succeed. More subtle errors can be more troublesome because they hide in your code and steal hours of your time, slowly degrading performance while you wonder what the problem is. A good solution here is to test the gradient computation part of our code, just as a developer would unit test portions of their code. We'll combine a simple understanding of the derivative with some mild cleverness to perform numerical gradient checking. If our code passes this test, we can be quite confident that we have computed and coded up our gradients correctly. To get started, let's quickly review derivatives. Derivatives tell us the slope, or how steep a function is. Once you're familiar with calculus, it's easy to take for granted the inner workings of the derivative. We just accept the derivative of x squared is 2x by the power rule. However, depending on how mean your calculus teacher was, you may have spent months not being taught the power rule and instead required to compute derivatives using the definition. Taking derivatives this way is a bit tedious, but still important. It provides us a deeper understanding of what a derivative is, and it's going to help us solve our current problem. The definition of the derivative is really a glorified slope formula. The numerator gives us the change in y values, while the denominator is a convenient way to express the change in x values. By including the limit, we are applying the slope formula across an infinitely small region. It's like zooming in on our function until it becomes linear. The definition tells us to zoom in until our x distance is infinitely small, but computers can't really handle infinitely small numbers, especially when they're in the bottom parts of fractions. If we try to plug in something too small, we will quickly lose precision. The good news here is that if we plug in something reasonably small, we can still get surprisingly good numerical estimates of the derivative. We'll modify our approach slightly by picking a point in the middle of the interval we would like to test and call the distance we move in each direction epsilon. Let's test our method with a simple function x squared. We'll choose a reasonably small value for epsilon and compute the slope of x squared at a given point by finding the function value just above and just below our test point. We can then compare our result to our symbolic derivative 2x at the test point. If the numbers match, we're in business. We can use the same approach to numerically evaluate the gradient of our neural network. It's a little more complicated this time since we have 9 gradient values and we're interested in the gradient of our cost function. We'll make things simpler by testing one gradient at a time. We'll perturb each weight, adding epsilon to the current value and computing the cost function, subtracting epsilon from the current value and computing the cost function, and then computing the slope between those two values. We'll repeat this process across all of our weights, and when we're done we'll have a numerical gradient vector with the same number of values as we have weights. It's this vector we would like to compare to our official gradient calculation. We see that our vectors appear very similar, which is a good sign, but we need to quantify just how similar they are. A nice way to do this is to divide the norm of the difference by the norm of the sum of the vectors we would like to compare. Typical results should be on the order of 10 to the minus 8th or less if you've computed your gradients correctly. And that's it. We can now check our computations and eliminate gradient errors before they become a problem. Next time we'll train our neural network. So far we built a neural network in Python, computed a cost function to let us know how well our network is performing, computed the gradient of our cost function so we can train our network, and last time we numerically validated our gradient computations. After all that work, it's finally time to train our neural network. Back in part 3, we decided to train our network using gradient descent. While gradient descent is conceptually pretty straightforward, its implementation can actually be quite complex, especially as we increase the size and number of layers in our network. If we just march downhill with consistent step sizes, we may get stuck in a local minimum or flat spot, we may move too slowly and never reach our minimum, or we may move too quickly and bounce out of our minimum. And remember, all this must happen in high-dimensional space, making things significantly more complex. Gradient descent is a wonderfully clever method, but provides no guarantees that we will converge to a good solution, that we will converge to a solution in a certain amount of time, or that we will converge to a solution at all. The good and bad news here is that this problem is not unique to neural networks. There's an entire field dedicated to finding the best combination of inputs to minimize the output of an objective function, the field of mathematical optimization. The bad news is that optimization can be a bit overwhelming. There are many different techniques that could apply to our problem. Part of what makes optimization challenging is the broad range of approaches covered, from very rigorous theoretical methods to hands-on, more heuristics-driven methods. Yann LeCun's 1998 publication Efficient BackProp presents an excellent review of various optimization techniques as applied to neural networks. Here we're going to use a more sophisticated variant on gradient descent, the popular Broyden-Fletcher-Goldfarb-Shano numerical optimization algorithm. The BFGS algorithm overcomes some of the limitations of plain gradient descent by estimating the second derivative or curvature of the cost function surface, and using this information to make more informed movements downhill. BFGS will allow us to find solutions more often and more quickly. We'll use the Bfgs implementation built into the SciPy optimized package, specifically within the minimize function. To use Bfgs, the minimize function requires us to pass in an objective function that accepts a vector of parameters, input and output data, and returns both the cost and gradients. Our neural network implementation doesn't quite follow these semantics, so we'll use a wrapper function to give it this behavior. We'll also pass in initial parameters, set the Jacobian parameter to true since we're computing the gradient within our neural network class, set the method to Bfgs, pass in our input and output data, and some options. Finally, we'll implement a callback function that allows us to track the cost function value as we train the network. Once the network is trained, we'll replace the original random parameters with the trained parameters. If we plot the cost against the number of iterations through training, we see a nice monotonically decreasing function. Further, we see that the number of function evaluations required to find a solution is less than 100, and far less than the 10 to the 27th function evaluations that would have been required to find a solution by brute force as shown in part 3. Finally, we can evaluate our gradient at our solution and see very small values. This makes sense as our minimum should be quite flat. The more exciting thing here is that we have finally trained a network that can predict your score on a test based on how many hours you sleep and how many hours you study the night before. If we run our training data through our forward method now, we see that our predictions are excellent. We can go one step further and explore the input space for various combinations of hours sleeping and hours studying, and maybe we can figure out an optimal combination of the two for your next test. Our results look pretty reasonable, and we see that for our model, sleep actually has a bigger impact on your grade than studying, something I wish I had realized when I was in school. So we're done, right? Nope. We've made possibly the most dangerous and tempting error in machine learning, overfitting. Although our network is performing incredibly well in our training data, that doesn't mean that our model is a good fit for the real world, and that's what we'll work on next time. Last time we trained our neural network and it made suspiciously good predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. Before we celebrate and begin changing our sleep and study habits, we need some way to ensure that our model reflects the real world. To do this, let's first spend some time thinking about data. Like a lot of data, our input and output values come from real-world observations. The assumption here is that there is some underlying process, and our observations give us insight into that process. But our observations are not the same thing as the process. They are just a sample. Our observation says that when we sleep for 3 hours and study for 5, the grade we earned was a 75. But does this mean that every time you sleep for 3 hours and study for 5, you will earn a 75? Of course not, because there are many other variables that matter here, such as the difficulty of the test, or whether you've been paying attention in lectures. We could quantify these variables to build a better model, but even if we did, there would still be an element of uncertainty that we could never explicitly model. For example, maybe the test was multiple choice and you guessed on a few problems. One way to think about this is that observations are composed of signal and noise. Nate Silver, the guy who correctly predicted the US election results for 50 out of 50 US states in 2012, wrote a great book on exactly this. The idea is that we're interested in an underlying process, the signal, but in real data our signal will always be obscured by some level of noise. An interesting example of this shows up when comparing the SAT scores of students who take the SAT both junior and senior year. Right on the College Board's website it says, the higher a student scores as a junior, the more likely that student's subsequent scores will drop. Why would this be? It seems like students who did well junior year would also do well senior year. We can make sense of this by considering that SAT scores are composed of a signal and a noise component. The signal being the underlying aptitude of a student, and the noise being other factors that affect test scores. Basically, if the student had a good day or not. Of the students who did well the first time, we expect a disproportionate number to have had a good day. And since having a good day is random, when this subset of students have a regular or bad test day on their next test, their scores, on average, will go down. So if we can convince our model to fit the signal and not the noise, we should be able to avoid overfitting. First we'll work on diagnosing overfitting, and then we'll work on fixing it. Last time we showed our model predictions across the input space for various combinations of hours sleeping and hours studying. We'll change our data a bit to make overfitting more obvious and retrain our model on the new dataset. If we re-examine our predictions across our sample space, we see some strange behavior. Neural networks are really powerful models, and we see here that all that power has been used to fit our data really closely, which creates a problem. our model no longer is reflective of the real world. According to our model, in some cases studying more will actually push your score down, which seems unlikely. Hopefully studying more will not decrease your score. So it appears our model is overfitting, but how do we know for sure? A widely accepted method is to split our data into two portions, training and testing. We won't touch our testing data while training the model, and only use it to see how we're doing. Our testing data is a simulation of the real world. We can plot the error on our training and testing sets as we train our model, and identify the exact point at which overfitting begins. We can also plot testing and training error as a function of model complexity and see similar behavior. So now we know overfitting is a problem, but how do we fix it? One way is to throw more data at the problem. A simple rule of thumb, as presented by Yasser Abu-Mostaf in his excellent machine learning course available from Caltech, is that you should have at least 10 times as many examples as the degrees of freedom in your model. For us, since we have 9 weights that can change, we would need 90 observations, which we certainly don't have. Another popular and effective way to mitigate overfitting is to use a technique called regularization. One way to implement regularization is to add a term to our cost function that penalizes overly complex models. A simple but effective way to do this is to add together the square of the weights to our cost function. This way, models with larger magnitudes of weights cost more. We'll need to normalize the other part of our cost function to ensure that our ratio of the two error terms does not change with respect to the number of examples. We'll introduce a regularization hyperparameter, lambda, that allows us to tune the relative cost. Higher values of lambda will impose bigger penalties for high model complexity. If we train our model now, we see the fit is still good, but our model is no longer interested in exactly fitting our data. Further, our training and testing errors are much closer, and we've successfully reduced overfitting on this dataset. To further reduce overfitting, we could increase lambda. And that's it. We've trained and evaluated an artificial neural network to predict your score on a test based on how many hours you slept and studied the night before. I've really enjoyed making these videos, and I wanted to say a big thank you to everyone who's watched and commented. I want to point out that supporting IPython notebooks are linked below and available at welchlabs.com/blog. To be kept up to date on future videos, you can subscribe below and follow me on Twitter. Thanks. Last time we trained our neural
If you found this post interesting and useful, please hit the like button, and I'll see you next time.